All right, let's talk about a hidden force that's shaping our world literally every second of every day: thermal conductivity. I mean, this is the reason your coffee gets cold, it's why your computer doesn't just melt into a puddle, and it all starts with a very simple and kind of weird question. So picture this. You go into your kitchen drawer, right? You reach in and grab two spoons. One's metal, the other's wood. And that metal one feels way colder. But wait a minute. They've both been sitting in the exact same drawer at the exact same room temperature. How is that even possible? It sounds like a trick question, but it's not. It's actually the perfect window into what we're talking about today. Well, the answer to that whole spoon mystery, it comes down to a concept called thermal conductivity. And we're about to see exactly how this fundamental property of matter explains that chilly feeling. Okay, so what is it exactly? Thermal conductivity, which you'll almost always see represented by the letter K, is basically just a measure of how good a material is at moving heat from one place to another. You can think of it like a heat-moving skill rating. Some materials are absolute pros, and others are, well, they're total amateurs. To really get our heads around this, let's picture a classic physics experiment. You've got a slab of some material, could be anything, metal, wood, you name it, and it's sandwiched between a hot surface on one side and a cold one on the other. Now, we all know heat is going to flow from hot to cold. That's just how the universe works. But the real question, the important one, is how fast does it move through that slab? And this is where it all just clicks into place. There's a brilliant analogy from the famous textbook Transport Phenomena that puts it perfectly. It says, heat slides downhill on the temperature versus distance graph. Just think about that. It's like a ball rolling down a hill. The steeper the hill, the faster the ball rolls. That slope is everything. And boom, just like that, our spoon mystery is solved. For a high conductivity material like that metal spoon, the temperature hill is incredibly steep. The instant you touch it, heat just rushes away from your warm hand into the metal. That's the cold sensation you feel. But for a low conductivity material like wood, the hill is really, really shallow. Heat just trickles away slowly, so it doesn't feel cold at all. So here's the kicker. The metal spoon isn't actually colder, it's just a much better heat thief. Okay, so we know what conductivity is. We get the big picture. But how does it work, really? I mean, what's going on down at the microscopic level? To understand that, we have to take a journey deep inside these materials. Well, it really depends on the type of material. In gases, it's basically like a game of pool, where molecules are just bumping into each other and transferring energy with each collision. In nonmetal solids, think wood or glass, the energy travels in these little waves called phonons that vibrate through the tightly packed atoms. But metals? Oh, metals are playing a completely different game. Yeah, their secret weapon is a whole sea of free-moving electrons. They're not tied down to any single atom, so they create what's basically a superhighway, zipping all over the place and carrying energy with incredible efficiency. This is exactly why the Wiedemann-Franz Lorentz law exists. It just says that for pure metals, if something is a good conductor of electricity, it's also going to be a good conductor of heat. It makes perfect sense, right? The same superhighway of electrons is doing both jobs. So this huge difference in how heat moves creates a massive divide between materials. We can pretty much sort everything into two big camps: conductors, which move heat really well, and insulators, which, don't. And when I say a huge divide, I'm not exaggerating. The range is just staggering. Pure metals can conduct heat thousands of times better than gases can. It's not a subtle difference. It's a massive, massive gap in performance. Let's put some real numbers on this. Take a look here. You've got copper, a fantastic conductor, with a K value of around 384. Now look at wood, a classic insulator. It's all the way down at about 0.126. And then you get to air. Air is a terrible conductor, with a K of just 0.026. The difference is it's enormous. To put that into perspective, this means copper can conduct heat almost 14,000 times better than plain old air. That is the power of that electron superhighway we were talking about. It's just no contest. So this massive difference isn't just a cool science fact, right? It's a fundamental principle that engineers use every single day to design the world that we live in. When you want heat to move, you grab a conductor. Think about it. A cooking pan is made of metal because its entire job is to get heat from your stove into your food as quickly and efficiently as possible. Or look at the heat sink on your computer's processor. It's made of copper or aluminum specifically to pull that damaging heat away and keep it from melting. And on the flip side, when you want to stop heat dead in its tracks, you use an insulator. That's why the handle on that metal pan is made of wood or plastic to protect your hand. It's why we fill our walls with fiberglass insulation. And it's exactly how a coffee thermos keeps your drink hot for hours. The whole point is to trap heat and tell it, you're not going anywhere. But here's where things get really, really clever. We can actually start to engineer our own materials by combining things. We can create something new that has an even lower conductivity than its individual parts. Basically, we can design the perfect roadblock for heat. So, how do you make a fantastic insulator like styrofoam? Well, it's a pretty simple recipe. First, you start with a solid material that's already a pretty poor conductor. Then, you trap tiny, tiny pockets of a gas like air, which we already know is a terrible conductor, all throughout it. The result is this composite material with incredibly low thermal conductivity. You've basically built the ultimate heat trap. So we've got a great handle on conductivity now, but in the real world, things aren't always so simple and static. Heat doesn't just flow steadily. It changes, it moves, things get complicated. So to handle all those dynamic situations, engineers need a couple more specialized tools in their toolkit. First up is something called thermal diffusivity. Now here's the key distinction. Conductivity tells you how well a material can move heat, but diffusivity tells you how fast a temperature change will spread through it. So if you heat up one end of a long metal rod, how quickly does the other end get hot? That's diffusivity. It's all about the speed of a heat wave. Now let's make things even more complex. What happens when the material itself is moving, like a fluid? Imagine you're stirring a pot of hot soup on the stove. Which one do you think spreads through the soup faster? The swirling motion from your stirring or the heat coming up from the burner at the bottom? Believe it or not, there's a specific number that gives us the answer to that exact question. It's called the Prandtl number, and what it does is directly compare the spread of motion, or momentum, to the spread of heat in a fluid. And this number is absolutely critical for engineers. If you're designing a car radiator or modeling a hurricane, you have to know which effect is going to dominate, the physical movement of the fluid or the transfer of heat within it. The Prandtl number is what tells you. And that brings us to a final, pretty fascinating thought. We've seen how we can control the flow of heat by choosing the right materials, and even by engineering brand new ones. So, what's the next frontier? Could we one day engineer a thermal switch? I'm talking about a material that, on command, could instantly flip from being a perfect conductor to a perfect insulator. The quest to fully master this unseen flow of energy is, believe me, far from over.